We started our discussion on series system reliability with the simplest possible configuration of a series system, namely two prismatic bars connected in series, axially loaded by the same force P. In that context, we looked at the effect of dependence among the two member strengths and also uncertainty in the load. Let us continue with that line of inquiry, but let us bring in more elements higher than 2, and let us give the option of not every member being loaded by the same force at the same level. So a 2D determinate truss gives us just the right platform for that. So we look at a 5-member truss, a square truss with one diagonal, and we will consider a few cases. So here are the scope of the problem and all the random variables. So we have one horizontal force. Each element can fail either in compression or in tension. Failure is defined in terms of stress. The stress magnitude in failure, whether in tension or compression, the magnitude is the same, and the behavior is linear elastic. So it's as simple as things can get. The element limit state is yield times area minus the member force, and the system limit state, the system failure, is the union of these element failures. So as I said, we'll look at 4 different cases. The first case is only the load is random, log normal with a certain mean and COV, and in this case all the member properties including yield strength are deterministic. All the 4 sides of the square have the same area and the diagonal is a little thicker. In case 2, we introduce randomness in the member strengths. The Y's, all the yield strengths are all random, but they are the same, so they're identical and fully dependent. H continues to be random as before, and the cross-sectional area, they are as defined before and non-random. In case 3, we go to the other extreme for the member strengths. Instead of being fully dependent, now they're fully independent. So they're mutually independent and identically distributed. So here we have 1 plus 5, so 6 random variables. And in the final case, we go to the midway. So H is random, the A's are deterministic, but the member strengths are partially dependent. So they have the same correlation coefficient between each pair of 0.5. So let's look at what happens in each of these 4 cases, and let's also set up and solve the problem. So in case 1, a very simple structural analysis gives us all the member forces. So we have in the column on the right but 1 the load magnitudes, and if we compare that with the member strength, which is area times yield, we can find the probability that the strength will be greater than the member load Fi, and on the very right column, that's why you see we have listed the member reliability. In member 1, there is no force. That is a consequence of the kind of loading on the structure. In member 4, there is also no load, so those 2 members have full reliability. There is no possibility of failure. And for the other 3 members, members 2, 3, and 5, the member reliabilities are, as you see on the right column, 0.985, 0.985, and 0.948. It would be tempting, as is done in cases of a series system with independent elements to multiply all these reliabilities and come up with the system reliability. That would not be right, because in structures we are sharing the same load between the elements. We have to be cognizant of that. This is the system performance event. The system is safe, the complement of the system failure, and that is all the member limit states are positive. And that, written in terms of H, is given as the intersection of those 5 events, as you see in the first line of that equation. H less than infinity is basically saying that y has to be greater than 0. So that is obvious. There is no possibility of failure in members 1 or 4. And for the others, you see H has to be less than 200 kilonewton for member 2. H again has to be less than 200 kilonewton for member 3, and less than 169.7 kilonewton for member 5. And now, since we are looking at the intersection of these events for the system safe performance, the intersection is H is less than 169. So it in effect becomes a single element problem once we take into account the repeated appearance of H in all these limit states. And now we are able to introduce a log normal nature of H. We have been doing this sort of thing in element reliability computations, so we know that quite well, and that can be given, the answer can be given in terms of the normal CDF evaluated at log of 169.7 minus the logarithmic mean divided by the logarithmic standard deviation, and the answer is 0.95. Obviously, if we had naively multiplied the member reliabilities, we would get a pessimistic answer. It would be obviously a wrong logic, and the system reliability would end up being 0.92 in that case, but that would be the wrong answer. We move to case 2 next, and case 2 is we allow all the yield strengths to be random, but it's the same yield strength for all of them. So all the 5 strengths are completely dependent. Here in this table we have listed the limit states, and we again look at the system safety event. That given in terms of the y's, h and y's, h being for the first member and the fourth member, there is no failure obviously. So looking at members 2, 3 and 5, the most stringent condition is h is less than 0.85 y. The reason we can say that is that both h and y are non-negative quantities. So h less than y and h less than y and h less than 0.85 y, the answer is h. The intersection is h less than equal to 0.85 y. So again, h and y being log normal random variables, we can convert that limit state into a single limit state involving a normal random variable, and that is what you see in the next line. We again come down to a single normal CDF. The beta value is 1.29 and the reliability is 0.90. So from the earlier value of 0.95 we come down to 0.90, and in the end we are going to look at all the 4 answers, 4 cases together and see how they all fit together. Let's move on to case number 3, which is all the yield strengths are now mutually independent. So in case 2 they were all the same, now they're all mutually independent, and that unfortunately we are no longer able to convert the system safe performance event into one single limit state, but we have to now take into account the fact that all the y's are different. So y2 and y3 and y5 are different random variables, and the 3 events are also not independent because h is common to all of them. So we have to be careful of that fact, but it's also true that h and y, they're all log normal, so we can guess that we are now looking at 3 dependent normal safety margins. So that gives us 3 safety margins in terms of in terms of M2, M3 and M5. M2 being defined as log of h minus log of y2 because we want to go to the normal space, and likewise for M3 and M5, and that gives that lets us compute the mean vector of the m's and the covariance matrix of the m's. The way we do that is, if you want to work out the longhand, the covariance or the correlation coefficient can be computed as you see on the screen, and then we are able to go back to the joint CDF of M2 less than M2 at 0, M3 at 0 and M5 at 0. So that intersection of the three events has a probability of 0.87, and we compute that using the multivariate normal function, which we know how to do in MATLAB. So it further comes down to 0.87. In the fourth case, we allow some dependence in the member strengths, to be specific, a row of 0.5 between each pair. So we proceed as before. We have three safety margins: M2 less than equal to 0, M3 less than equal to 0, and M5 less than equal to 0, and we want to look at the intersection of those three events. And we are able to find the mean vector and the covariance matrix. While computing covariance, we have to also take into account the dependence between the y's. So y2, y3, y3, y5, y2, y5, and etc. So we do that, and we have the results here. The mean vector of the m's and the covariance matrix of the m's are, as you see on the screen. If you wanted to know how to do that, I have given one example for M2 and M3, where you see that row of 2, 3, so which means row between the y2 and y3 also need to be listed in this case. And finally, the answer comes to 0.89, so it goes up from the complete independence case. So putting together all these 4 cases, we find that when h is the only random quantity, the member strengths are non-random, then we have the highest RSIS. And then when we allow randomness in the member strengths but consider them to be fully dependent, then it comes down from 0.95 to 0.90. When we allow partial dependence in the member strengths, then it further goes down to 0.89, and when they are fully independent, all the member strengths that is, then we have the lowest system reliability of 0.87. And this is actually evocative of what we have already discussed in the beginning of this discussion on series reliability, looking at the two-element 2-bar system that we looked at. Here on this graph, you see a row on the x-axis, and as we saw in all those 4 cases of different load magnitudes, that as dependence increases, system reliability goes up, system PFSIS goes down, so reliability goes up, and as we go towards independence, PFSIS goes up, which means reliability goes down. And this is exactly what we saw in the case of this truss as well.